the recording. Okay, so this week, last week's exercises, I have compiled the model answers here. You guys, you just do this. Oh, it's going to do this weird thing now. Apparently, you're probably seeing this strange line here, like I am. So I'm going to do this. And there. All right. So the first question of this week's exercise was a fitting theme. We have a plastic tube fitted in a ventilator, and the attachment is produced by a machine that has tolerance of sigma equals 0.04 millimeters, meaning that the variances of the thickness of the tube is, well, there's a weird wording here. The variance of the thickness of the tube is 0.04 to the power of 2 of those. So this is the standard deviation of the or tolerance. Usually when we have a machine of some sort, and instead of a variance, we talk about standard deviation, because the standard deviation is, you can think of it as the expected deviation from the mean in either direction. 74 attachments were measured to have an average thickness of 7.874 millimeters. So we want confidence intervals, both 95% and 90% confidence intervals for the expected thickness of this attachment piece. So we've measured, what's the situation here? We've got a sample, and we have a 75, n equals 75 size sample, and we have gotten a result which is 7.874 millimeters. And what is the interpretation of the 95% or the 90% confidence interval? It's that, again, let me reiterate this. We did this during the lectures, and I did this on the Friday. And sorry about the missing recording on Friday. There was my laptop ran out of disk space, and it didn't warn me. I have cleared since enough space to make sure that this doesn't happen, but it didn't provide any warning. And for some reason, even the partial recording was not, it was corrupted in some way. So, but we talked about this. So the interpretation here being is that we give a 95% confidence interval. That means that if we have a tolerance of, well, a standard deviation of 0.04 millimeters, and if we use that to calculate an interval such that 95% of the cases fall in this interval. So if we take the average, then 95% of the time, this interval, look, the interval itself is the random variable. It's not, the average here is random, and from that random variable, we derive another random variable, which is the interval. Its endpoints are here, and that's your average. So whenever you have an average, it gives a different result. And this random variable, which now is really an interval, it's an interval such that 95% of the time that interval falls in such a way that the actual expected value is within those limits. So there's only a 5% chance that the actual, that this interval is such that the actual expected value is outside the interval. So we turn this around a little bit, and we say that we're 95% confident that the actual expected value is in this interval, but that's not actually true. I mean, if we have to understand the difference. If we calculated this interval hundreds of times, then 95% of those cases, which would be such that the actual interval is contained, the actual expected value is in this interval. But this interval, we don't know. Now, recall that if we do the 95% confidence interval, so what we are looking for, again, I've drawn a picture like several times already, but let me draw another picture. Oh, sorry. Oh, I seem to be missing. Just a second, I'll get my pencil. So we want the limits in such a way that our Z alpha over 2 is in the 0, 1 distribution, such that again, I've drawn it like this. Oh, no, I'm not seeing the picture. Just a second. Why am I not seeing? Oh, there it is. So you see here, again, one more time. So the Z alpha here, we set that limit into in such a way that over here we have half the probability, and over here we have half the probability. So the middle region is 95%. So that's why this is 2.5% and this is 2.5%. That's why we get the lower limit and the upper limit. Here I'm using MATLAB and I'm using the norm inv. And now because this is 0, 1 normally distributed, I get the lower limit at 0.025, the upper limit at 0.975. And I get these two limits. This is minus 1.96, this is 1.96, if this is the picture. And I'm going to be using those in that I'm going to reverse I'm now reversing the calculation because we normalize the variable. We showed it on lectures, right? So we normalize the variable by removing, subtracting the expected value, dividing by the variance. And here we do it the other way around. Sorry, dividing by the standard deviation, not dividing by the variance, standard deviation. The standard deviation is the standard deviation of the actual distribution divided by, of course, the square root of n, because we have n data points here. So we get the limits, and the confidence interval falls in between 7.8649 and 7.8831. If we want to calculate the second one, we can do it directly. I mean, I've done it like here directly. I'm calculating here. This is 0.04, that's the sigma. This norm inv is now these two values. And I'm dividing those values by the square root of 75, because my n is 75, and I'm adding 7.874 here, which is the sample average or sample mean, and I get the limits here like this. I used here 0.05 and 0.95 because this is in the second one. It's the 90% confidence interval. So in here you have to understand the 90% is the region that falls between this 0.05 and 0.95. So anything above this and anything below this has a probability of, well, the joint probability of being outside this region is now 10%. It's not that huge. I mean, in a way, there's a 10%, in a manner of speaking, there's a 10% chance that the actual expected value is somewhere outside this region. All right. But you see here, both this depends on the variance or the standard deviation and the sample size. Well, because the sample size appears here, then if we know the variance and we know the confidence limit that we want, we can in fact look for a certain, what is the sample size if we want the confidence interval to be within certain ranges. So here, for instance, consider the previous question. We want a 95% confidence interval in such a way that the interval length is 0.005 units, in this case millimeters. So we want within 95%, we want 95% certainty that the expected value is known up to 5 micrometers, I think. Yeah. How large a sample do we need? Well, we can slip this in. Oh, there's apparently, let me just change that for you. Wrong window. Oh, this is the previous one. Oh, just a second. I had a typo there. The bar was missing something in that answer. Yeah. Bar and bar. Right. And then what? Ah, sorry. Okay, now we have the bar there, right there. All right, sorry about that. So, look, we know the confidence interval is this. It's the average minus that. We know the average should be something. We don't even care what the average is, because if we calculate the difference between the end points, so if it means we take the higher end point and subtract the lower end point, then really what we get is 2 times z alpha over 2 times sigma over the square root of n. So we don't even care about the average. Of course we don't care about it, because we are only looking for the n here. So that's the one sanity check that you need, is that this shouldn't depend on the sample. The sample average is there, but we don't really care about the sample average. That is what it is. We want the n. So the 2 endpoints, their distance is 2 times z alpha over 2 times sigma. And if we use the same z alpha over 2 as we had before, that 1.96 here, then we can solve this for n. So we solve this first for square root of n, divide by 0.005, this here. And of course, this square root of n needs to be greater than that, and we get n greater than this. We put these numbers, alpha, remember alpha was 0.05, so we already calculated the z alpha over 2. Sigma here is 0.04, and we divide this all by 0.05. We get n greater than or equal to roughly 983.4. We're really only interested in the integer value of this, and because this is greater than 983 point something, then we conclude that the sample size must be at least 984. So it's got to be pretty big. I mean, think about this. This is accurate. The distance between the previous one, the distance between this is 0.02 roughly, less than 0.02. So we want about 20 times, no, 1/10, 0.02. So yeah, we don't even want that much accuracy. We don't even need that much accuracy. We need about fourth, 1/4. We want to cut this down to 1/4. So we end up multiplying this by what? 15, something like this, 10, 15, 13. Yeah, almost 15, almost 15. And 14 something. So yeah, well, it depends on the square root of this. So yeah, you would expect that. So it's quite a bit bigger sample size is needed, and larger sample sizes are needed if we want to push down the uncertainty, the confidence interval. But that's what you would expect. I mean, the variance here determines quite a bit, and this only depends the inverse of the square root of n. So pushing it down by a few more percent may require larger n's. All right. Let's move on. So this is, I mean, this is an example of having to understand how the confidence interval works. I'm going to give you the use of this confidence interval formula and all these interval formulas and all the estimator formulas. It's no use here trying to make you learn by heart, remembering all those formulas. Yeah. Roughly, yeah. Yeah, that's a good question here. So I'm wondering what the mistake was there. Probably, you know, you had the wrong Z, or maybe you rearranged the formula divided by 2 or divided by something. Yes, it's definitely not something to worry about too much. Wrong numerical answers should not subtract from the points if they are easily pointed out or easily verified, such that okay, you made a mistake here, and the calculation and the logic goes and depending on the reviewer, they may subtract 1 point from here. You should definitely get at least 1 point if you calculate it correctly, so that you get the upper lower idea correctly. Then you should definitely get at least 1 point. You should be able to recognize that it comes from the interval. If you made a small mistake in the rearrangement, then depends a little bit on who's reviewing and where it is. I can't say for sure, but at least 1 point should be awarded. That's definitely so. Okay, let's move along. Unless you have other questions about these two. Let's move along a little bit. So this is from the famous Albert Michelson, so known the Michelson-Morley experiment. If you are familiar with physics, they measured the speed of light at different places, and they had thought that maybe there would be variation on the speed of light depending on which direction you are measuring it, because the Earth is rotating. So if it's rotating this way or that way, then the speed of light might have, you might get different results for that. And they came to the conclusion that the speed of light is invariant of the relative movement. And then they came to the conclusion that, I don't remember exactly what the conclusion was, that it was very confused by this and so forth. And I think Einstein's special relativity took this into account with the Lorentz contraction and all that stuff. I'm not going to go in depth there, but they measured the speed of light, and let's say that they measured it 100. I have no idea whether these are accurate, but you know, the speed of light was measured. It was pretty accurate because the standard deviation in his samples was 79.01 kilometers per second. Given that it's about 300,000 kilometers per second, the speed of light, then this is actually not a big difference. This is definitely less than 1 in 1,000. It's about 1 in what? 1 in 3,000, I think. No. Well, yeah, roughly that. And if you think about this, yeah, 1 in 4,000 roughly. Yeah, that's true. 1 in 4,000. Assuming that the measurements were normally distributed, well, assuming schmooming, formulate the 95 and 90% confidence interval for the variance. Now, remember, the variance is, we can come up with the idea that the sample variance, because you calculate the squares of certain variables, add them together, and each of those squared variable itself is a bit like a normally distributed variable, because you're taking the average, you're taking the value minus the average, and the average is pretty good an approximation for the expected value. So if xi minus x bar, it's roughly, not quite, but it's roughly equal to x minus mu. There's a slight difference, and that's where the n minus 1 comes from. If you remember that formula where we derived it, that's why we divided by n minus 1 instead of n. And we proved that the sample variance can be thought of as a sum of squared normal distributed variables, but not quite n minus 1 of them. Because the last one is really, in fact, the sum of all of them, and it's subtracted from there. But so we have, by normalizing now this sample variance by multiplying by n minus 1 and dividing by the actual variance, we get a random variable. This is now a random variable because the s squared is, in fact, a sample standard deviation. So it's a random variable because it depends on the outcome. And this random variable has a chi-squared distribution. And with n minus 1 degrees of freedom, this normalized variance, if you will. And from this, we can derive the test statistics, because, you know, we proved it or showed it during the lectures again. So if you think about the idea that this value is chi-squared distributed, and it's between h1 and h2, then solving for this in such a way that only this sigma squared is left at the middle, we get an interval n minus 1 s squared over h2. Notice how the upper limit is here as a divisor because it's the larger value. N minus 1 times s2 over h1, where it's the lower value. So this leaves sigma squared between these two values. And now, because the chi-squared distribution is not symmetric, I drew pictures of it. The chi-squared distribution is, I'm not very good at drawing them, but it's something a bit like this. I'm definitely not very good at drawing them, but it's something like this. So it's and it's got this. If we are looking for these two regions, then these two regions are not symmetric. They're something like this. And we calculate one at 0.025 and one at 0.975. This is from the cumulative distribution. So this gives the H1 at 73.3611. It means that 2.5% of the cases, the value is lower than this. And in 2.5% of the cases, the value is higher than 128.433. So this gives H1 and H2. These are the upper and lower limits for that. So it means that in the chi-squared distribution, again, here's your H1, here's your H2, and 95% of the time the variable is in this region. So hence the interval in which 95% of the time the actual variance would land is this. And then we calculate this in this particular sample. We get 4,812 and 8,424 for these statistics. These would be the variances. And now if we calculate the confidence interval for the standard deviation, of course, we take the square root of this because remember, this was standard deviation, sample deviation in this case. And then this means the sample deviation, the actual deviation, standard deviation falls between these 95% of the time. So the deviation would be 95% confidence interval would be 69.37 and 91.78. There's a pretty, there is something of a sanity check. The S you get in this, it should be between these two values, the actual standard deviation from the sample, it should be between these two values, and usually it's closer to the smaller value than the larger value because it's not a symmetric distribution. But is it the 95% confidence interval? The deviation is somewhere around here. Now for the 90% confidence intervals, well, we just simply use, you should get points. I mean, now look, if it's the type of error where you use different, well, if it's 0.90975, that's, well, yeah. In this case, don't be sorry. But then you would get out. Let me guess. You got a really narrow distribution somewhere here in 69. This would be the lower limit, then roughly, or the upper limit would be just a tad bit larger than this, right? I mean, you should definitely get a point from this if you use the correct formula. The rough guideline for this week's exercise is the correct formula should give you 1 point, and then mistakes in calculation subtract points if they are relevant. In this case, it should be relevant because if you think about it, you'd probably get your interval such that your sample deviation is not in fact even between those. The lower limit is probably right. The upper limit is probably too small. Yeah. Not sure how it's going to play out, but one thing for sure, I mean, you could easily verify that if the sample standard deviation is not between the two values you get, then you should double check that always. Because I mean, I've said this many times over during the lectures and here in exercises, you should always make these small sanity checks. You know, complete accuracy now, not necessarily completely check everything, but these sanity checks you should be able to do in such a way that if you come up with this confidence interval and your sample value is not between these two values, then definitely you calculated something wrong, right? So I'm not going to say whether or not you're going to lose some points there. If you got the lower limit right, then probably you should get your points and all that. But really, that's a sort of mistake that is easy to avoid, especially if you got this value so much off that this sample value does not fall between this confidence interval. So it's hard to say. But if you think about in the exam, if you get a confidence interval that does not contain your sample value, then you're not going to get full points, at least there. That's, it's because it's so easy to check. I'm very tolerant of mistakes made from computation, but sanity checks that are easy to do, you should always do them, because this is something that you should be able to understand, at least. That it's also a way to measure understanding. If you get a value, if you get an confidence interval that doesn't even contain the sample value you get, then it means that you haven't, well, it doesn't mean it, but it lets me to believe that you might not have understood the nature of the confidence interval. Okay? Not going to say very definitely how it should be, but I'll think about that. I'll make some more a detailed recommendation for the grading here. The same thing we do here, but with 5%, we get narrower. Let's see, here's another sanity check. This confidence interval should be narrower. So we can claim that because that's your sample variance or sample deviation is there, and these are more tighter limits, we can make this claim that, okay, it's probably close to this value, but that's, you lose a little bit because you get a narrower value, but then there's a higher chance of you being wrong. The chance of you being wrong, 10%, 5%, that's roughly the alpha you are using, but not going to go in depth into the philosophy of this. I mean, I by now should have understood that there's a slight reverse thinking here. Right? Any other questions regarding this? Okay, feel free to shoot any questions you might have, and so and just talk about this. The question number 4. 500 households were interviewed and asked if they have subscribed to a certain channel. 340 answered that they had, which means then that 160 didn't. What is the 95% confidence interval for the percentage of households that actually subscribe this channel? So, this is like saying, what is the probability that a random household subscribes to this channel? What is the 95% confidence interval for that? So now we are having a Bernoulli variable. This is very often the case that we are looking for. This could be the situation, for example, when you are asked whether you would vote for a certain party and so forth. So you would think it in terms of Bernoulli variable. It's not exactly like that. That polling questions and those have a slightly different way of doing the confidence intervals and all that, because then usually what you have is you have some parties and you're asking which one of them would you vote for and so forth. So there's a slightly different there, but let's say that this is conducted like an image consultancy company and conducts a survey or wants to say what percentage of people might be willing to vote for your presidential candidate. So you given the 500 households, you get 340 who say they yes. And what is the 95% confidence interval here? So we have a Bernoulli variable, yes or no. And we can think of this as being binomially distributed. We can think of this as having 500, n equals 500, and p is what we are looking for. P roughly somewhere around 0.68. And the confidence interval here, again, with this binomially distributed variable, remember that if we have a binomial distribution here, then our The expected value is n times p, right? That's your n times p. So hence p is, you know, the number of successes over n. That's your this hat p means that now this is the estimate of p, and the estimate for the variance, which was it's n times p times 1 minus p, right? This is what we are having. But because we are calculating the one for the one Bernoulli variable, so that would be the variance for the whole thing, and it's got n repetitions, so we divide that by n. So the variance is p times 1 minus p over n for that single variable. That's your variance. And then for that, the estimate for the variable of the single variable, of course, is p times 1 minus p. Well, n times p times 1 minus p is for the binomially distributed variable, which is this whole thing. So for the one variable, it's n times p times 1 minus p over n. So the n cancels out. And then, of course, we do the sample variance here, just like here. Look, it's just like in the previous one here, the square root of n, right here, and that's your standard deviations, the square root of your variance. So in this case, single Bernoulli variable variance is this p times 1 minus p, and we're dividing by the square root of n. So the variance is the square root of that. So we're just taking the square root of the whole thing. And we are now, this is binomially distributed variable with a very large n and a p that is somewhere in the mid region. So it's not very close to 1, not very close to 0. So we are thinking that this is approximately normally distributed. But if we take, remember that this was our x, then what we really want is the single Bernoulli variable here. So it would be what we get as 0, 1 distributed would be x minus np over the square root of so that would be roughly that would be roughly n01 distributed. So if you remember from there, this is from the material directly. So we derived from that in this case, this case we get here the z alpha over 2 again, just like before. So here variance, or variance over n, and take the square root of that times z alpha over 2, and then subtract that from the average or the estimate for the probability. And good old Z0 to 5, we got it of 1.96. We already calculated it before for the previous question. And putting these numbers in here, we get this. I can show you the MATLAB code here. I calculated it here before, I think. No, I don't have it here. Here I calculated it, right? Yeah, that's true. I'll show this. I had these calculations before. So here's I set this pH to 340 over 500 as here in this question. So 340 over 500, and then there's my pH for p hat. So that's my square root of pH. That's my lower limit. Sorry, that's the interval. So here's my lower limit pH minus that, and upper limit pH plus that, the same square root of in the formula, and I get this result 0.6391 and 0.7201. So you'd say that 95% confidence interval is somewhere between 63 and 72%, or 60, roughly 64 and 72%, somewhere over there. %68 in this thing. So you see, it's not terribly, it's not bad, but you know, it's not terribly certain either. I mean, it's 5% in both directions, almost 4% in both directions. All right. Here again, minor deviations from this, but you should understand here that this is simply an application or a special case of this same thing as here, except that now our estimated variable is the probability, the proportion or the probability, the p in that binomial distribution, and this we get by p times 1 minus p, the square root of that. That's the variance. All right. Any questions regarding this question? If not, then we'll move on. So we're going to question number 5. A certain country was studied, and we picked 50 men at random. Their height was measured in centimeters, and sample mean was 178.15. Sample standard deviation was 5.92. Assume that the height is normally distributed. Determine the 98% confidence interval for the expected male height in this country. So in this case, we don't know the population's variance. We only have the standard deviation from the sample. And in this case, we have to use the t distribution. Remember that this is exactly the same formula as in with the known variance. The difference here is that instead of using the actual variance, we use the sample distribution. What was I doing? The sample standard deviation, or the square. Sorry. Thanks. I didn't know this. Good. Because I don't, yeah, sorry. Is that better? Thanks for pointing this out, because it doesn't, my view here doesn't show which screen I'm sharing. I made a blunder there. Thanks for pointing it out. I will always point out if I'm talking about something. So, okay, let's move along. A certain country was studied, 50 men were picked at random. The height was measured in centimeters. Sample mean was 178.15. Sample standard deviation 5.92. Assuming normally distributed height, determine the 98% confidence interval for the expected male height in this country. So, because we don't know the population variance, the only thing we have is the standard sample deviation or the derived sample variance. We have the same statistics, the same formula really. It's just that now we will be using the t distribution instead of the N01 distribution, because we don't know the variance. So the variance itself is a random variable, and that means that it's a wider distribution because there's more uncertainty. And for the 98% confidence interval, we calculate the minus 0.01 probability and the plus 0.01 probability here. And so anything below the 1% threshold and anything at the highest 1% threshold will be outside these. We can use t-inv. That's the t distribution. The t distribution only has one parameter, which is the degrees of freedom. And in this case, we use n equals 49 because we have a study which had 50 men. So remember that because the standard deviation is calculated with n, with using the use of the average over n and then divided by n minus 1, then n minus 1, in this case 49, is the value that we are going to be using. Should have used different symbol for that. I didn't use n for 50, so my n is now 49. So the confidence interval is just like that before, and we got the t from the t in. It's about 2.4005. And multiplying by 5.92, dividing by the square root of 49, which just happens to be 7. We get 176.14 and 180.16 as the upper and lower thresholds here. So within about 4 centimeters, we know this. And the important thing to understand here is that you use the t distribution instead of the n01 distribution. If we use the norm inv here, we could do that with the norm inv. We'd get a wrong result, of course. We'd calculate the 0.99 norm inv, and we'd get Z statistics of 2.326, about 2.33, and that would give us a narrower interval, but that would be wrong. Okay, so understand that you have in the t distribution you need to use well, understand that when you need to use the t distribution, you will get a wider region or a wider confidence interval. And it's not wider only because if you have a smaller n, it's wider because this divisor here is smaller, but also because this comes from a distribution that is wider. So it's like a double whammy for small n. It becomes wider and wider for small n. And which it should be, because then your estimate here for the standard deviation or for the sample variance, your estimate will be worse quality if you have a smaller n. All right, moving along. Any questions regarding this? You have to understand the difference between this question number 5 and question number 1. Understand why question number 1 and question number 5 are different. Compare them and understand it. Comes from the fact that in 1 we know something something more about the distribution that is not part of the sample. In here, the only thing we have to go on with is the sample, so we don't know the variance. And that's why our estimate of the variance is a random number, so it becomes a wider confidence interval. Remember that the wider the confidence interval, the less certain we are about the value. Well, sorry. The higher the certainty, the wider the confidence interval, because, of course, if we say that it could be anything infinitely wide, then obviously we can say that with 100% confidence. On the other hand, if we don't need quite as much confidence, if we are willing to tolerate the 10% chance of error, then we can calculate the 90% confidence interval, we get a narrower interval. All right, moving along. Question number 6. This already introduces us a bit to next week's topics, which we will start talking about tomorrow at the lectures. And I already downloaded the next week's and actually the complete lecture slides, if you will, are already there. When I say complete, they're not necessarily complete in the sense that there may be some errors that I'm going to fix when I notice them. But mostly the topics are now there. So we have one final topic after this, and this question number 6 already starts talking about that a little bit. So let's say that we've established that in a certain school A, the points of the students that they get in their final exam is a random variable with expected value 32 points and standard, the standard deviation 7, but variance of 49, and it's normally distributed roughly. And we have one unknown school 25 students, we don't know which school this is from. We have 25 students who took the final exam and they had a sample mean of 29 points. So we're asking what is the probability that students from school A could get a result like this or worse? If you had to guess, would you say that the students came from school A, and why not? And I would really like for us to discuss this a little bit. This touches on a little bit of a philosophical question, and this kind of a question cannot be escaped by fancy mathematics. We can answer this probability question, but the interpretation of what do we know now cannot be escaped by use of mathematics. Instead, we need to talk about what can we assume, and that's not part of this question really, but we have to talk about it a little bit. But let's say, firstly, when X has this distribution, if we had this X from this school, then a 25% sample from this school would have a distribution where it would be the expected value of 32 and the standard deviation the variance of 49 over 25, because that's how the variance goes down as n goes bigger. So the average would have the expected value the same as an average, just your one person from the school, but it would have a variance that is far smaller. And the numbers are deliberately chosen, so it's 7 over 5. The standard deviation is 7 over 5. So the probability that we are looking for is the probability that this X average is smaller than 29. We can now normalize. We can normalize this. So subtract from 29, subtract the expected value, divide by the standard deviation, which is the square root of this. So that's 7 over 5. So we get that this normalized variable should be, the probability that X is this small is the same as this normalized variable being smaller than or equal to this. And this comes out at minus 2.14. So because this is a normal distribution, we can get here from the norm CDF or from looking for the table, the Z value at 2.14 on the N01 normal distribution. And that comes out at 0.9838 roughly. And we get that this is the probability that we are looking for is 0.0162. In other words, if the students are from school A, the probability of getting a result that is this bad or worse is about 1.6%. So now, I'd like for us to spend a little time on thinking about how do we interpret this result, because this applies to all those confidence intervals and next week's topics when we do these testing, statistical testing. We calculate a test variable pretty much like we would calculate the endpoints of a confidence interval. And then we come up with a hypothesis and we either accept it or reject it based on how probable it is. So this is the probability is 1.6% that the result like this emerges if these people are from school A. But this is an open-ended assumption. Yes, if they are from school A. But what if we have another school, B, or C, or D? We have several schools. And we know something about those other schools, their averages. And for argument's sake, let's say that all those other schools have a higher expected number for this grade. What would you then say? Would you conclude that it's likely that it's not from school A? Let's say we choose between A and B. We have two schools. It's either from A or from B. In A, the expected number of points is 32 with 49 variance. In B, The variance is the same 49, but the average number of points is 40. What do you think? Which school would have the higher probability? Obviously A, because A has a lower expected value than B. Okay, this is rare. This is a bad result for students of school A. Yes, rare and bad, but it would be even rarer if we had a higher expected value. Alternatively, take another example. We have a school B, which we are comparing. Is this group of students from school A or school B? Let's say that in the school B, the average, the expected number of points is 31, but the variance is very, very small, much smaller. Let's say the variance is, instead of 49, it's 25, the variance. If we now do this and calculate it with this, then we get a far smaller probability for that school, because it's got a much smaller variance, right? It's much smaller variance, even though the average is a little bit is a little bit smaller. Still, this result would be even more anomalous for that school. So you have to understand that when we make such an open-ended assumption about how to interpret this, this is only that if they are from school A, the probability is 1.6%, if we assume they are from school A. But we usually cannot say what the probability is there if they are not from school A. So it has to be understood that very often the statistics that we make and the probabilities that we calculate are under some certain assumption. And people act often, or they act, meaning they make decisions often based on the idea that, okay, this is the sort of information we got, which is legit here. But we didn't get here the information that there's a 90, I mean, the worst that comes to worst, I mean, there's a 98% chance that it's some other school. No, it's not. Where the value 2.19 comes from? Well, 2.19 comes from the fact that 29 minus 32 divided by 7/5. So it comes from here. So if you calculate this, that's your normalized, I mean, it's here. We are 29 is the result. That's the sample average. The expected value would be 32. We're dividing it by what the variance should be. Yeah. Or not variance, but the standard deviation should be 7/5. If we're doing this part here, that's minus 2.14. And this here, because that's your average, we're subtracting your sample average, we're subtracting the expected value, calculating the standard deviation. So this x bar minus 32 over 7 divided by 2, this quantity here is an N01 normally distributed variable. So this is the normalized version of that. And now because this is symmetric, then this is Z smaller than this. It's like we are, again, we are doing it here. So the probability of it being in here is the same as 1 minus the probability of it being here, because this is symmetric. So we're doing that 1 minus there. Usually these negative values are not always put in tables, only the positive ones. So, but because we can get that by using 1 minus that, then we can calculate the negative value as well. Yeah, thank you. Aha, okay. Yeah, that's good. That's good. So I would like to stress here that this is a fantastic place to be critical if you understand what is going on. Um, I mean, why I dislike, when we were talking about what courses do you want to teach, and I said I wouldn't prefer not to teach statistics. The reason is, statistics, when you study it a little bit, there is a very easily gotten illusion that you understand what's going on. You can calculate these probabilities, and when I can teach you to calculate these probabilities, but then when you calculate these probabilities, you will be thinking that, okay, I now know that, for instance, here, I can give a 98%, 98.4% chance that this is some other school. No, it's not. It's not that. It's just that if they are from the school A, then the probability is 1.6% here. And this is one place where you can use Bayesian analysis. You could dig out, for instance, the variance and expected value of all other schools. If you know the all other schools, the whole country average over schools has a smaller average and a higher or a higher variance, then you could do this for every other school. You could do this for this school, and then you could have the probability that just in general, and the probability that it's not in A, and probability that it's somewhere else. You could use Bayesian analysis to come up with a more reasonable answer to this question. So I'm not a Bayesian in the sense that I think that Bayes formula and Bayesian analysis is a end all be all of everything. But I do think that this kind of approach should be taken instead of just throwing these p-values around. We'll talk about this in the lectures tomorrow. Are there now any questions regarding these 6 questions? Okay. If there are no questions here from anyone, I'm going to just end this session here, and hope to see you guys tomorrow at 10 a.m. All right? All right. Yeah. Question 3. Okay. Get to the final values. You mean this? All right. I'll change to MATLAB and I'll show you that how it's done. Right. I actually did it already beforehand. I double checked the results. Just a second. You see my MATLAB screen here. So what I did first, okay, so yeah, okay, I haven't got it. So let me just go there. I'm just clearing this room. So, all right, let me go there. So I'm going to just punch in the numbers here from that question. So we had Albert Michelson's where n equals 100. So I'm going to put this n as 100, and then I'm going to do the whole thing here. So I'm going to give my S as 79.01. That's my S. My alpha, because I'm doing the 95% confidence interval, so my alpha is the 5%, so it's 0.05, right? So I am going to calculate first H1 as the chi-squared inv from, and now my n was 100, so I'm going to use n minus 1. And I'm looking for the statistic for the lower part. So that's would be alpha divided by 2 and n minus 1. That's directly from there. So I get 73.3611 for that H1. And then H2, that's the alpha, but I get 1 minus alpha over 2 and n minus 1. So I get 120. So those are the results that I get. Now that's the upper and the lower limit in my chi-squared distribution. And now I need the upper and the lower limit. So my interval is as it's n minus 1 times s squared divided by h2. I divide by the higher number, so I get the lower end of the region. And the upper region is n minus 1 times s squared, over h1, right? So I get the interval here. That's the interval. That's 4,800 and so forth, and 8,000. That's my interval. And then to get to the actual standard deviation, I take the square root of the interval. So I get 69.37 and 91.78. Yeah. Because, I mean, look, the interval in this question, the interval gives you the confidence interval for the variance, and then looking for the standard deviation, which is the square root of the variance. So if the variance is between these two numbers, then if the variance is between these two numbers, then the standard deviation is between these two numbers with that 95% confidence. Does that answer that? Yeah. So that answered your questions, I hope. Good. Any other questions like this? Please feel free to ask whenever you have some kind of a question that is like that has like this. If anything puzzles you or you are worried that I don't fully get why those numbers come from, I can always open up the argument and make it more clear and step by step and break it down to smaller steps. Whenever you feel confused or anything, just say. Okay, you use different application. What did you use then? Did you use a different software or different? I have no idea what that is. TI, that's your calculator, the pocket calculator, right? Do I understand this correctly? Or that programmable calculator? Ah, okay, okay. So
Actually, can you hear me?
I can hear you. Yes.
Oh yeah, awesome. So I use the student software version of the calculator.
Yeah.
And it gives me a bit of different results when compared to MATLAB when I checked it with today. Like, will that be a problem? Because like
I don't
in
think
my
it will be a problem, but double check one thing. Is your confidence level, are you using the confidence level correctly there, for instance? Are you using I'm not sure what kind of command you are using there. What kind of command does it have for doing this? Does it directly calculate the confidence interval?
Hold on, I'll try to show it somehow.
Let me see if I can.
Well, yep, just give me a moment, please.
I can make you a co-host of this meeting. So if you are able to share, you should be able to share now.
All right, I'm just like opening the app right now.
Okay, because then I can answer probably the question a little bit better.
Yep, yep. All right, let's share the screen. Oh no, this one.
Okay. Oh yeah.
Yep.
Yeah.
All right. Okay, so I have this like okay,
Yeah.
I have this kind of thing which comes from statistics, confidence intervals, and I use like
The
Z
Z, yeah, the
interval,
Z, yeah.
and I
So the
have the
Z
confidence level
interval,
right here.
that's, yeah. So if you got a slightly different result there from that. This doesn't seem to have, let's show the statistics part yet still. What is there?
All right.
And stat tests, just the statistic, go back to the one where the tests. Just show
Tests.
the statistics before you choose anything. Just take the drop
Okay, yeah,
down menu, yeah,
statistics. Yep.
and then take the confidence intervals.
Yep.
So there's Z interval, T interval, two sample prop. This doesn't seem to have the variance interval here. This doesn't seem to have the variance interval. So if you call, you don't, this doesn't seem to give you the possibility to calculate the question for the confidence interval for the variance. Because this has the Z distribution, the T distribution, and then you have these regression intervals. We don't talk about regression here, but this doesn't seem to have the one for the chi-squared statistics. So if you use this,
basically how I use this is like I calculate all these like okay, let's start with the first question. Yeah. So basically I calculate it as we calculated like on paper.
yeah,
Like taking the alpha and everything.
yeah,
And
yeah.
then
That seems
after
to
I
be
get
correct.
this part,
Yeah,
huh?
yeah,
Yeah, after I get to this part, I use this like calculator to calculate basically these.
yeah. Those values, yeah. So you
And
get
then
is
these
that,
are
is
the
that
values I get.
different from mine?
This is a bit different, I guess.
Let me see what. Let me just compare it quickly. Which question is this? This is the.
This is the first one.
Let me just compare it very quickly.
All right.
Oh, wrong. I had wrong. Just a second.
Yeah.
This co-host thing is not familiar. 7.6. I think 4.9. I think you got the same result as mine. I mean, within one digit. Yours has one more digit here.
Yeah.
So it's susceptible to small rounding difference, but your result here is 7.86495, and mine was 7.8649, and I had truncated it. It's possible that the next digit is 4, and then the following is something like 6 or 4 and 5. So it's rounded it differently. But it seems like this is so close that it's more or less correct, right? I'm pretty sure that this is correct from your point of view. It's probably just has more significant digits there.
Okay, all right, then that's no problem there.
Yeah, but your software doesn't seem to have the direct calculation for the, but if you did it by hand, then I wouldn't worry about it.
Well, I basically used
two
both times.
Are correct, then I wouldn't worry about anything.
Okay.
All right. Good.
Thank you.
You're welcome. Any other questions here? The question about will the course end? So what we will do here is we will have a Tuesday lecture this week, but because of the Easter break, it's been scheduled and we have not rescheduled anything, even though we are in this lockdown mode. Wednesday, starting Wednesday, we will have a week off, and the course will end. Let me see. This is the 6th, so we have no, it will not end next week. We have one more set of exercises, which will be held 2 weeks from now. And then in the last week, I'll have a Q&A and recap. But other than that, we probably won't have any new material. So all the material will be handled by Wednesday next week. So it's not going to be the last. The lecture is the last lecture with new material will be the following Wednesday. That's true. So that would be, let me just check the calendar. So we have, tomorrow is the 7th, we have a lecture. Then we have the break. We have the 15th, we have a lecture. On 17th, we have the exercise session. On the 20th, we have the second exercise session, the last exercise session. And then I think on the 21st of April, I will host the last lecture with a Q&A, and we'll go through some of the materials, and I'll try and inform everyone about every possible thing that might be there. But yeah, the Wednesday 22nd, we will not have lectures, and the 24th on Friday, we probably won't have any exercise session then either. Yeah. All right. Thank you, everyone. I'm going to stop the recording now. It's been a pleasure, and I hope to see you guys again tomorrow.